Hi everyone, this is Isaac Nuttall, and I'd like to tell you about my Data Analytics Unit 4 project. So right here, I've described crucial terms such as linear regression models and what a least squares regression line is, and basically the fundamental difference between a correlation and a regression is that while a correlation just focuses on an association or relationship between two variables and whether they just happen to go together, a regression focuses directly on how one variable causes another, on causality. And it wouldn't be helpful to do regression analysis on something like the effect of how much gasoline you have on how far your car can drive, because that has a direct mathematical relationship. You need something with a little more ambiguity as to what the cause is, because regressions can help to discern those kinds of relationships. So, a scenario where a regression analysis might be helpful is, say, determining the effect of poverty rates on crime, and vice versa. It could also be reverse causality. And with linear regression assumptions, linearity and normality are both pretty straightforward. With homoscedasticity, we can't have it be that all of the data points are clustered together at the beginning and then they start fanning out later on. We need the variance to be constant. And no multicollinearity, we can't have one variable being used to predict the other. They need to be independent of each other. No endogeneity, we can't have a relationship between the independent variable and the error. The error must be constant. And no autocorrelation. Errors cannot be correlated with each other. And with a coefficient of a constant, that is our y-intercept, that's our starting point of the data. The independent variable, the coefficient of it, is the predicted increase in the dependent variable for every 1 unit increase in the independent variable. Standard error, how different the population mean is likely to be from our sample mean. The t-statistic, which is the ratio of departure of the estimated value of the parameter from its hypothesized value to its standard error, or in a nutshell, how statistically significant are the individual values in the data set or variables. And the F statistic, it is not listed here, but it's how statistically significant our overall model is, or that's what the p-value of the F statistic is. And the p-value of the t statistic from the independent variable is the chance of finding a value at least as extreme as the one found when the independent variable is used as the predictor. And right here, we explain R squared and adjusted R squared. R squared is just how much variability in the data can be explained by our model, with adjusted R squared penalizing for the use of additional variables that don't add much. And right here, we talk about what are the independent and dependent variables we'll use in these cases and how to interpret each of these different values. Then right here we put linear regression into practice. We import the necessary libraries and dependencies, we load the house data CSV, and right here we can see the first 5 values and information about what each of the data types are. And we explore relationships between variables. We see square feet above and square feet living have a strong correlation. Not so much, though, for price and square feet above, or square feet above and square feet of living. And therefore, we have square feet of space above as our independent variable and square feet of living space overall as our dependent variable. We plot each one of them on a scatter plot. Then we perform a regression and we see our results right here. And our R squared is pretty good. Our model can explain over 70% of the variability in our data. And we interpret these results right here and use it to predict new values. And we do pretty much the same thing with our multiple linear regression, except we use multiple variables. And as we can see right here, we perform our regression in R squared, and adjusted R squared goes up, meaning that with the new independent variable of price, in addition to square feet of space above, we are able to better predict what square feet of living space is. So price, it adds more value. It's not just an extraneous use of variables. And once again, we interpret our model and use it to predict values. And now it's on to time series. And with time series, we examine a stationary time series dataset, which has a number of different data points going along different points in time. And right here, we can see quarter consumption, income production, savings, and unemployment from 1970 all the way to 2017. We import the CSV, we perform some data wrangling like dropping extraneous columns, we import matplotlib, we look at the time series as it's plotted along time with each one of the variables having its own graph. And we also visualize each of their relationships with a pair plot. We can see which have more strong correlations than others. We then pre-process our data. Right here, we make sure to get the data we want into specific tables so we can perform more operations on them. And importing PDREMA for some reason did not work, but we were able to import stats models and access the crucial tools we need to perform time series analysis. So right here, we go through our model diagnostics and make sure that each one of our assumptions are valid. And as we can see right here, there are no residual autocorrelations. Like, for the most part, they remain in the range. And there's no excessive skew or kurtosis. Most of the modes or groupings of data remain in the middle, showing that the data is largely normally distributed. And there is largely residual constant variance with, for the most part, things not moving out of the way in huge amounts compared to where they would everywhere else. It's pretty constant variance throughout. And right here, residuals versus fitted values randomly scattered, they stay pretty much in the middle for the most part. There are some outliers. And with the diagnostics convenience function, we can see several different graphs plotted out here, including one that shows normality with a diagonal line going across. And the closer these points are to the diagonal in the middle, the more normally the data is distributed. And then we perform some scenario forecasting right here. We plug in the data and we're able to see the forecasted value for each of the values we have over here in 2019 quarter two. And as we can see, this is the predicted change. And with a 95% confidence interval. And right here, we can visualize the effect of the unemployment rate changing using the get forecast method and see it graphed, and it's showing within a 95% confidence interval where we expect unemployment to be within the very near future following 2019, which can be used to make crucial decisions. All right, thank you all so much. I hope you have a great rest of your day.